Hello, welcome to these tutorials on programming computational fluid dynamics. My name is Saurabh. Alright, so let's continue with our code. Today I'll be continuing with the code and we'll try to finish this code for linear advection equation. Before I forget, recently I have seen a video from Professor Lorena Barba. I'm talking about this video, finite volume solutions to hyperbolic PDEs, and there are a couple of more lectures associated with this one. So you should certainly go through these videos. It will help you to grasp some of the concepts, especially related to the Riemann solvers, which I'll be using in the later section of this videos. Okay, so let's continue. So the last thing that we had done during the earlier video was writing the solution to a file, and we also saw a code in Python for reading this file and then plotting the solution. Okay, there are a couple of things I would like to do. First of all, in the config file, I'll change the base path to another folder called out, so that the results do not get cluttered here, especially during maybe today during the later section, or in the next video we'll be creating some animations to see what is happening intermediately during the course of solutions. So during that time it will be nice to put it all in one folder. So to do that, let us change this base path to one folder. I have also created a folder in the directory. So here I have created a folder called out inside the directory in which I have been working on. So I have created this folder here, and also I have changed the base path. And now let's continue with our solver. So the next thing was to set time equal to 0. So let me do it just one line before this one. So let me say time equal to 0. Obviously I'll have to tell that it's a double, and just to be consistent I'll change this to time, okay, because the time, that is what we are passing to the solution file, so that it can print it out. The next thing what we have to do is to set a variable called last time step equal to false. Let me just copy that just to save time. Yeah, today also during these videos I will also fast forward these videos at particular times, so that it will save a little bit of our time, especially the portions when I'll not be talking. Okay, so let's do the next step. The next step is to write the for loop here over the iterations, the time iterations. Okay, so let's write that. For I equal to 0, let us name it as time iteration equal to 0, and it should go up to config dot number of time iterations. So this many time iterations will be done if it does not break out of the loop using this variable. Okay, so the first thing that we do is calculate dt. So let us say double dt is equal to, okay, let us not calculate the dt here, but calculate it in another class. That will help us, not now. Now it's of not much of any importance, but when we go to two-dimensional mesh, this function might, this particular functionality will grow in size, and it is better to put it in a different place. Now it's going to be a very small thing. Okay, so to do that, let me create one more class. Okay, there is one thing which I have not done and it should be done. That is, we have to define something called advection velocity because we are solving the advection equations. So let me go to config here and insert another variable called advection velocity. And let us make it equal to 1 for now. So basically all the waves, that is actually there is only one wave here which will be traveling at a velocity of 1 meters per second. As I already had told, the units are going to be SI. So this is 1 meter, this is 1 meter, this is 1 meter per second, this is 2 seconds, and so on and so forth. What I have done here is I have assumed that dx is a constant, so I have taken the first cell and I have taken the value of dx from that cell. Okay, the assumption is that dx is already been also set up and it is constant. So let me just write it. Okay, there is one more thing which we have to define inside our config file, which is the courant number. I think we have also not defined that. So let us go to our config file and define the courant number as well. Okay, at this point of time we have our dt defined. Now let me look at the next step. Okay, so what I have done here is first of all I have calculated dt, then that is delta t basically. If the time plus dt is greater than the stopping time, that means that that particular time step that we have taken is crossing the stopping time, and therefore dt has to be adjusted such that now this will be our last step, and also the last step size is reduced and it is going to be equal to the current the stopping time step minus the current time. Okay, and here in our code will be written the remaining code. So let us look at the next. Yeah, also what I have done is I am incrementing time, and if it is the last time step, then I am breaking out of this loop. Okay, now the next step is to do these steps. So for the number of RK steps, we will be doing this. The first thing is to apply the boundary conditions. Basically, applying of boundary conditions will be done through ghost cells. So let us write our class first, which will be doing this. So we'll be applying periodic boundary conditions, which means that we will be copying this and this value into this and this ghost cell. Similarly, we will be copying this and this value into this and this ghost cell. Okay, let us implement that part now. So 0 and 1 will be made equal to this and this cell. So let us see which cell is this. So this cell, if you see, is equal to ni plus ng. This cell is ni plus ng. So this cell is going to be equal to ni itself. Okay, let us do it by counting. Let us understand that by counting. So this should be 10, right? Because our ni here is 10. If you remember, it's if starting from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this is 10 and this is going to be 11. So basically this cell is going to be equal to number of internal cells. This is going to be equal to number of internal cells plus 1, and then continuing depending on how many number of ghost cells are present. Okay. So let us do that. In NetBeans, if you want to change any variable name after you define it, you can press Ctrl R. Oh, it's not changing, right? Let me see. If I go to source, okay, let me right click and try it out. So if I say refactor, rename, Ctrl R should work. I don't know why it's not working. Oh, I think it's not working because I'm using this screen recorder. The same thing, the same shortcut is used by screen recorder as well. And I hope that I have not paused it now. Okay, let me see. So I can change this to ghost cell because I'm working on one ghost cell at a time. Okay, this is going to be RK step. Let me just check. I hope I have not made a mistake here. RK step. This is going to be ghost cell RK step. Okay. Also, this has copied the left hand side ghost cells. Also do it. Let us also do it for the right hand side ghost cells. So those are going to be okay. Looks fine. So let us look at this. So this are going to be the cells after the number of X cells. If you remember, number of X cells plus the ghost cell index, that will take us. Oh yeah, I think I made a mistake here. It should be plus number of ghost cells. Yeah, now it seems alright. Let me put this on a different line so that it becomes a little bit more good to see. So the number of X cells plus the number of ghost cells plus the ghost cell index itself, that is coming from here, is equal to the value inside that should be equal to the left hand side values which are inside the domain. So that is going to be the number of ghost cells plus ghost cell. Yeah, that seems to be all right. Okay, so let me put a blank line there. Okay, everything seems fine here. So let me repeat again. So what I have done is I have copied these values here. Ghost cells are 2, so these two values I have copied here, and these two values I have copied here. I hope things are okay. If not, we will realize it while running this code. Let's let's continue. So at this point of time we should call that ghost cell updater, which will set up our boundary conditions. Okay, the next thing is reconstruct variables. So as we have been doing, let us create one more class for that. Okay, this statement has become really very big. So what I have done here is I am setting up this loop such that it goes from one cell inside the ghost cell towards left to up to one cell on the right hand side, which is inside the ghost cell, just outside the internal variables. Let us look at that. So I'm starting from this cell. So this is going to be equal to number of ghost cells minus 1. Similarly, this is going to be equal to this particular cell. Actually this cell is going to be equal to ni plus ng plus 1. Okay, so that we stop here. It is less than, right? I is less than. So I is less than this cell, so it will stop 1 for this. This is also looking a little ugly. Let us remove this. So so reconstruction, since this is first order reconstruction, we are just going to copy the values at the centroid towards the interface. Okay, now there are two ways of saving variables. I actually did not talk about it earlier. Let us talk about it now. So I have used these variables called uwest and ueast, which will be basically saving the I minus half and I plus half values at the interface. This is one way of doing it. Another way of doing it is to save just one variable, which is the derivative at the centroid. That is, if you are that is one way of doing it. This way which we have adopted is more general, in the sense that even if we are unable to calculate the derivative, then it is still fine. Especially if you look at some higher order reconstruction methods like WENO, then we don't get derivatives there. What we get is directly this interface values. So this is going to be a more general way. And say for example, in some methods the derivatives are what are calculated. In that case, you can always calculate the uwest and ueast values by doing a little bit of by using the reconstruction function. So this is a more general way, so we'll be adopting this way of doing it. I have seen many codes which save the derivatives, so if you have used those codes or looked at those codes, then you should not get confused as to what I am doing here. Okay, so let us set up those uwest and ueast now. And now at the beginning, let us just copy those values. So since this is first order, we will then be changing this functionality later on to use higher order methods. Okay, so the reconstruction part is done. Now the next thing is to calculate the flux. Okay, so here what I have done is I am going from edge index. Okay, let me just tell you what I'm doing here. Now flux is calculated at this interfaces, right, or edges. Oh, let me actually name it as, instead of saying edge index, let me call it, because it's not an edge basically, right, it's an interface. Let me remove index. Say, oh, I cannot name it interface because this is a keyword in Java. So I'll say, okay, interface index is fine. Vector. So for interface index, I'm going from number of ghost cells to this. Okay, so we are going from this interface up to this interface. Okay, so we actually did not even talk about this indices, so let us quickly talk about it. So this is 0. Oops. So this is 0, this is 1, this is 2, and so on and so forth. So we'll start with 2. What is 2? 2 is the number of ghost cells. Similarly, we'll stop at this. So we have to stop at this. What is this? Ni plus Ng. But we have to include this, so we will stop at this, which is Ni plus Ng plus 1. Okay, so we will basically be stopping at that index of interface. So that is what I have done here. Now let us calculate the flux. Okay, so here I am using Lex Frederick scheme, which is basically a simple upwind kind of a scheme. If you look at this, okay, I talked about upwind earlier a little bit. So it is basically taking the it is basically about taking the left state or the right state value depending on the direction of the advection velocity. So if you say that advection velocity is positive, that is the flow is from left to right, that is, sorry, the waves are moving from left to right, then we will be this is going to be positive. So since this is positive, this left state value and this left state value, this left state value with a positive sign because of this negative, this is always going to be positive since it's an absolute value. So this is going to become 2 times left state value multiplied by advection velocity, and multiplying it by 0.5 will give us the flux, that is basically advection velocity into left value. Same thing will happen if advection velocity is negative, then this term is going to be negative, therefore right value into this value is going to be negative, and this here with a negative sign outside, this is going to become negative as well. So we will get flux as minus, we'll get flux as minus right state value into the advection velocity. Okay, that seems fine. Yeah, now whatever flux we get, we have to add it into the cell. For this we have to define one more variable inside cell. Let us call it total flux. Let us make the total flux equal to 0 at the beginning of this, so that for every arc step we start with flux 0, then we will add whatever flux is coming from the left side of the cell and the right hand side of the cell, and then we will calculate total flux. Okay, so this here is going to be the left side of that interface. This is going to be the right side of the interface. So the total flux for that particular cell on the left hand side, it is subtracted, and the total the flux is subtracted from the total flux and it is added to the flux on the right hand side. This particular construct is truly speaking not required in case of one dimensional case, but it will be very easy to do it in case of two dimensional case. That's why I am implementing it in this particular way. Okay, looks fine to me. Let us now go ahead. Okay, so what's next? Update cell average. We are going to use a Euler time step here, we know that. So let us do this part. Okay, I'll take a break here and I'll continue in some time. Okay, so let's continue. We had reached to this point. So now we need to update cell averages. So since we are going to use simple Euler time stepping, that is single step Runge-Kutta method, so let us that will just be okay. Now this updating has to be done only for the internal cells. Okay, here we are using the Euler time step. So the value at the arc step plus 1, here we know arc step is always going to be 0. So 1 is going to be equal to 0. Since this is one step arc, in this particular case, when we go for higher order time stepping, it will be different. I hope I have done everything correctly. So this is plus, I suppose. So let me just have a look at how have I calculated the flux. So it's subtracted from the left and it is added to the right. So yep, yeah, looks correct. So this will be plus because flux is entering through the left face and leaving from the right face. So if flux is entering from the left face, it's going to be a positive. So I'll add flux if it is entering, and it will be subtracted if it is leaving. Okay, fine, looks okay. If something blows up, we should also come here and check whether this sign is okay, but I suppose it is okay. We shouldn't leave things on, obviously we should not leave things just on luck, so let us be sure about that. Now the next thing is flux has been calculated, I think. Yeah, that's it. I have to just add the final step here, that is update time step integration dot update cells arc steps and dt. Okay, so now one last step is remaining, that is the last step that is remaining is to copy this average from the last step to the first step. So once all the steps are done, we copy it from the previous time step to the current time step, sorry, the last arc step to the first arc step. So we can again create a class here. That's a silly name. Anyways, okay, seems fine. Copy to 0th arc step. Okay, looks like everything has been done. We will finally, after our time iterations are over, we'll write to the file. So solution file writer dot write solution file cells and time. Great, looks fine. Well, when I just looked at this, there was a file counter which is being shown. It should not be shown, so let us make it private. So we can make this as private. Better not to expose things which should not be exposed. So seems alright to me. Let us run and see what happens. So it has run and it should create two files. Let me see. Yeah, it has created two files. I'll just peek through what it has done, then we'll run the Python code and check what actually it has done. Some values have changed here, it has gone up, and the wave seems to have moved. Okay, so let us plot and see what has happened. I have made some changes in this file, this plotting function file. It actually reads now through all the files. This is a library called glob which is available, which allows us to read through a particular directory and also use wildcards while reading it. Then I've sorted those file names, and then I'm going through each of these files, and I am reading the file, and I'm then plotting it one by one, and I'm saving the resulting plot into a file by the same name, just replacing .dat by .png. And I am finally this is a program which is available in Linux, which you can use for looking at the pictures. Okay, so let me run this, and yeah, this is at time step 0, and this is the solution at the final time step. So everything looks to have gone okay. So this is at 0 and 2. So what has happened is this wave has gone through this full domain, and it has returned back from the left hand side, and it has reached here. So let us do one more thing just before stopping this video. Let us set stopping time as equal to 1, so we can see that this wave would have, not 1, sorry, 0.5, so that we can see that this wave would have moved a little bit. Basically, yeah, this wave would have moved a little bit and stopped somewhere here. So let us look at this. Let me also change the title to time equal to. So let me just run this once more. Yeah, so time equal to it shows, so that that's a little bit better to see. Now let me set this up. Let me say the stopping time is equal to 0.5, and let me run this code again. Okay, this is at 0.5 now. Looks okay. The center should be at 0.5 approximately. Okay, looks good enough. I think that's all I had planned for today. In the next video, we will look at higher order reconstructions. We can obviously see that there is a lot of diffusion which is happening here. If I look at this, this particular sides are getting diffused, right? That is because of two reasons. One reason is that I have chosen CFL of 0.8. If I use a CFL of exactly 1, then I'll exactly get this square wave. I should ideally get this square wave. Let us test this. Let us test it now. But this diffusion is there. So to remove this diffusion, it will be nice to use higher order methods that we will look at next time. I have not decided on which higher order I'll be using, which method I'll be using for higher order schemes, but I'll think over it, and let us look at that in our next video. Okay, so before just stopping, let us make our CFL equal to 1 and see what happens. So where is CFL? Here. So when we make CFL equal to 1, if we run this code, we should get exactly square wave. Yeah, so it seems that everything is fine. Yeah, one more thing. I said that I'll be doing reconstruction in the next class, that is higher order reconstruction, but I think I will instead, what I'll do is I'll create one more video wherein I'll be showing these animations, so that it will be much more clearer as to what is happening here, and I will maybe talk a little bit more about this overall code once more in the next video. Okay then, see you all soon.